electricity, and magnetism. Alright folks, welcome back to the next lecture in electromagnetism. Today we're going to be taking a look at the three fundamental particles of electromagnetism. What are those three particles? Well, let me go ahead and write them down for you, alright? So we're going to be analyzing all three of these particles. So on the first column, we're going to be writing down the particle's name. Okay, this is a bad marker. Next column, we'll be looking at the particle's mass. Okay, what's the mass of our particle? Mass is a very important concept, as well as the charge of our particle, and finally, the antiparticle associated with our particle. Okay. Let's go ahead and get started. So, first particle we'll be taking a look at is the proton. Proton. Now, the proton, as you hopefully know, is in the nucleus of an atom. Okay? And the proton has mass. What is that mass? It's going to be 1.67 times 10 to the negative 27 kilograms. Okay? The proton is very heavy, right? Compared to the electron. It's about 2,000 times heavier, or about 1826 if you want to be precise, times heavier than the electron. The proton also has a charge, okay? It's going to have a charge of... Well, it turns out the universe has this amazing property called the conservation of charge. That means charge always must be conserved. In a closed system, the total amount of charge always has to remain the same. We're going to touch on it later on more. But what you need to know for now is that the universe creates an antiparticle for every particle. Okay? A minus A for every A. An antiproton for every proton. And as a matter of fact, that's the name of the proton's antiparticle. It's called the antiproton. It has the exact same mass as the proton, but its charge is minus 1.6 times 10 to the negative 19. So, how can we denote it? We're going to denote it as P plus the hat. Okay, that tells us it's an antiparticle. The next particle up is going to be, of course, the electron, right? The proton is at the nucleus. The electron, of course, orbits the proton around. The proton, usually most protons have a charge that extends out to 10 to the negative 15 meters out of the atom, and that's been confirmed experimentally. And the electron is also going to have some charge and some mass. Its mass, of course, is going to be much smaller than the proton. Its mass is going to be 9.11 times 10 to the negative 31 kilograms. Its charge is, however, going to be the exact opposite of the electron, negative 1.6 to the negative 19 coulombs. And finally, its antiparticle, which is called the positrino, okay, that's going to be denoted as E minus to the hat. Or you can even write it as E plus, right? E plus. Whatever way works for you. And finally, what we're going to have, the final particle is the proton's neighbor in the nucleus, and hopefully you know who it is. It's going to be the neutron, right? That's going to be the neutron, ladies and gentlemen. Now, the neutron is going to have a certain mass. Its mass is going to be approximately the same as the proton's, 1.67 times 10 to the negative 27 kilograms. Its charge, it's going to have no charge. And its antiparticle is the antineutron. Okay, antineutron. And we can denote it as N to the 0 hat. Now, there's some very interesting stories here. Number one, notice the mass of the proton and the mass of a neutron are the same. Is it because they're both in the nucleus and they have to balance each other out? As a matter of fact, no. The mass of the neutron is a bit heavier than the mass of the proton for a very special reason. As you can see, the mass of the neutron is about 1%, more or less, heavier than the mass of a proton. Why does that matter, you might ask? Well, it matters because the mass is just a bit different. Because the neutron, when isolated, actually undergoes beta decay. So an isolated neutron actually turns into a proton and an electron, which, as you can see, if you add them up, they both add up to zero net charge. Okay? Now, if it was the other way around, and the proton was just a bit heavier than the neutron, what would happen? Okay, what would happen if the proton instead decayed by beta decay into a neutron and an electron? Okay, what would happen? Well, the universe as we know it wouldn't exist. Okay, why is that? Because everything in the universe is made of hydrogen. Hydrogen has no neutron. It only has an isolated proton. And so hydrogen's isolated proton would undergo beta decay. And so hydrogen would fail to exist. There would be no hydrogen in our universe. And yet every star in our universe, the living universe, us, me, you, we're made of star stuff. Every star in the universe, every planet in the universe is made of hydrogen. So where there is no hydrogen, there is no universe. And where there is no universe that has a neutron with slightly greater mass than a proton, our universe as we know it would not exist. And so that's why we need the neutron to be a bit heavier than the proton. Otherwise, the universe may not exist. Thanks for watching this lecture on electromagnetism. We'll check you out next time.